So our next speaker would be Mai Bui from Imperial College.
Thanks. Good afternoon, everyone. So today I'm going to present some work I did with my colleagues at Imperial College. The work we're looking at today is looking at opportunities for efficiency enhancement for BECCS systems. So this is a simplified diagram of the BECCS process. And for our work, before we start improving the efficiency, we kind of want to first identify where the efficiency penalties are happening in the process. So one key part is this CO2 capture process, which has a very high heat requirement for the solvent regeneration, and this imposes quite a high efficiency penalty. And secondly, when you're co-firing a power plant with biomass, biomass is considered a low-quality fuel, and as a result is a lower efficiency system compared to coal-fired power plants. And having a closer look at the fuel composition, you can see why. So with the two biomass types that I've shown here, there's a wood type and the herbaceous fuels, and you can see that generally biomass has much higher moisture content, and in addition to that, the lower heating value is much lower compared to coal, and as a result you have lower power generation efficiency. But there is a benefit when you're co-firing with biomass. It's got lower ash content compared to coal, and in addition to that, the sulfur content and the nitrogen content of biomass is much lower, so this results in lower SOx and NOx emissions. So this is an overview of the work that we did. So if you want further details about the methodology, it's been published in the two papers there listed. But overall, what we did, we assessed the performance of BECCS using a 500 megawatt ultra supercritical pulverized power plant using a 90% CO2 capture system. The key effects that we wanted to analyze was looking at different coal types, so comparing a high sulfur coal versus a medium sulfur coal, looking at different biomass types, so we used a herbaceous type of biomass, so wheat straw, and clean wood chips was the wood type. And then we also looked at varying the moisture content of your biomass. So we had 5%, 16%, and 50%. So the biomass co-firing proportion was also varied. And then lastly, looking at the CO2 capture technology that you're going to use. So you can use your conventional MEA system, which is not very efficient, or using these more advanced solvents, such as CANSOLV or biphasic solvents. And some of the key process parameters that we wanted to evaluate, looking at the combustion performance, so the adiabatic flame temperature, SOx emissions, looking at how much waste heat could be recovered from the flue gas coming out of the reboiler, and then lastly the energy efficiency and carbon intensity of your BECCS system. So the first part, we looked at modelling the combustion process. So these are the different scenarios. We combined the coal, the two coal types with the different biomass types at varying moisture content. So the scenario letters here that are listed here are going to be shown on the graphs later. So looking at the energy flows through a thermal power plant, we can see that there's a lot of areas where you lose lots of heat and lots of energy. And so from the perspective of a power generator, this is waste heat. But from a CO2 capture process, this could potentially be useful heat that you can use to supply heat for your CO2 solvent regeneration process. So this is the overall concept of what we wanted to achieve. So when the flue gas has come out of the boiler, it's typically around 370 degrees Celsius. So there's still quite a lot of useful heat in that flue gas. In some places you can use this flue gas to dry your biomass, but we also considered that in our study, but most of it was trying to see whether we can actually recover the heat using a heat recovery system, which is just a series of heat exchangers, and then seeing if we can supply enough heat for the CO2 capture plant, which typically needs a temperature of about 80 to 120 degrees Celsius. And so first looking at the combustion performance, so keep in mind this is the adiabatic flame temperature, which is just a theoretical temperature. in practice, you would never operate a boiler system or combustion system at these temperatures, but it's just to give you an idea on the effect of the biomass composition on the combustion performance. And what you see is that when you're burning very high moisture content biomass, you're not really improving the performance of your combustion system. But just by decreasing the moisture content of your biomass, you can actually improve the combustion performance. And there's opportunities here that if you have kind of a lower grade coal, for instance, that's very wet, you can co-fire with a low moisture content biomass and improve the combustion. And then in this case, when you're increasing the biomass co-firing proportion with these lower moisture content biomasses, you get more heat, so there's potential to recover more waste heat from your flue gas. Looking at so using our FACT-SAGE model, we had very detailed chemical compositions of your flue gas composition. So we looked specifically at the SOx emissions, and you see there's a very obvious effect when you're burning high sulfur coals versus a medium sulfur coal. So generally high sulfur coals will emit more SOx, obviously, and then low sulfur coal will have significantly less SOx emissions. And having a closer look at the SOx mechanism to kind of understand why this is the case. So when you're looking at the mechanism, you can see that it's the SO2 formation that's normally thermodynamically favored, but then you can shift the equilibrium by decreasing the temperature towards the formation of SO3. Also, the presence of iron oxide in the actual ash can catalyze this reaction as well. And then another aspect is considering the components in your ash. So a lot of studies, experimental studies, have found that alkali oxides in your ash can potentially react with the SOx and reduce your SOx emissions. So zooming into the high sulfur coal scenarios, what we see is that the trend is quite linear. So SOx emissions decreases linearly as you increase your biomass co-firing, and that's because as you're burning more biomass, you're reducing the overall sulfur content of your fuel composition, and so you decrease SOx emissions. And then looking closer at the medium sulfur coal scenarios, what we see is a much more staggered profile. So there's some equilibrium effects happening in this case. And so having a closer look at the chemical species that were being formed, we could see that what was happening when, if you kind of look at the wheat straw case on the to right here. So wheat straw actually had a higher sulfur content compared to the wood chip, but you see that there's a lot lower SOx emissions. And the reason, if you look closer, is wheat straw had a higher ash content, and specifically the components that were reacting with the SOx was the metal oxides, so your calcium oxide, magnesium oxide, and so forth. And they were reacting with the SOx and reducing the emissions. And if you look at the maximum amount of SOx that was being emitted in the scenario, it was actually below the tolerance level of your amine system. So you could potentially reduce your SOx emissions just by using a lower sulfur content fuel and then using the biomass to further decrease your SOx emissions, and then potentially not need flue gas desulfurization. So this here is showing the recoverable heat that you could get from your flue gas through waste heat recovery, and the key thing here, as you're increasing your co-firing proportion, so when you're burning more biomass, we find that we had to co-fire more biomass to meet our 500 megawatt power plant capacity. So when you have a higher fuel firing rate, you result in a higher flue gas flow rate, and so you can actually recover more waste heat. And that's why you can see here that in these higher biomass co-firing regions, you can get potentially all of your CO2 capture process heat requirements just from waste heat recovery. And then another effect we can see is that when you're using your different solvent types, they have different heat duty requirements. So with your using the MEA system at some co-firing proportions, you won't be able to get all your heat from the flue gas. But when you're using a more advanced solvent, which has much more lower heat duty, you could potentially, at all co-firing proportions, get all of your heating requirements from the waste heat in the flue gas. And so it's in this yellow region that we see that BECCS could potentially operate at zero efficiency penalty, but obviously there will be a capital cost that is involved with buying and building these heat exchangers to recover this heat. So if we zoom into just the 50% co-firing range, and the reason we did that was because in all three solvent scenarios, we could recover all the heat from the flue gas. So looking at that scenario, well, we wanted to then compare the efficiency of those systems. And what we see is that there's a clear improvement in efficiency when you're using a better or more advanced solvent. So we could see from the MEA scenario, using this conventional system, you get about 31% efficiency for your BECCS power plant, but improving it further, you can get about 34% using an advanced biphasic solvent system. And then furthermore, you can have heat recovery, which brings your efficiency of your BECCS power plant to about 38%, which is actually 3% above the average power plant efficiency in the US and Canada. So this is quite an interesting finding. So this here is showing now the carbon intensity of your BECCS system. So what you find, so if we kind of look at the actual numbers at the 50% co-firing proportion, we see that as you're improving the efficiency of your BECCS system, you see you're being less carbon negative. And the reason is the efficiency, as efficiency increases, you're burning less fuel per megawatt hour. So you're actually capturing less CO2 from the atmosphere. So there's this kind of trade-off that's happening that Connie also mentioned and observed in her results. And the key thing is considering how this BECCS system will operate in an actual electricity grid. And what we see with power plants, the load factor of a power plant is a function of the power plant efficiency. So even though you have these higher efficiency systems, the reason these get dispatched more often is because the marginal cost of the electricity generation is lower compared to the low efficiency systems. So the efficiency of the BECCS plant will then impact its dispatch rate, which then in turn affects its potential to mitigate CO2. And so if you look here, to capture the same amount of CO2 that you capture with the MEA system, you have to operate at a higher load factor for the high efficiency biphasic system with heat recovery. And so the question that we ask ourselves is, what's the objective of a BECCS plant? Is it trying to be more efficient at generating electricity, or are we trying to be more carbon negative and capture more CO2? So you've got to kind of consider what these BECCS systems are going to do in a power system. And then another effect that a lot of work has been done by my colleague Mathilde in this space, looking at the carbon footprint of your biomass. And this is a key thing that you have to think about, because if you have a biomass that has a very high carbon footprint, you could potentially have a BECCS system that is carbon positive and not actually capturing any CO2 from the atmosphere. So you've got to limit the carbon footprint of your biomass that you're putting into these systems. And so this here is just showing the two examples for the biphasic and the MEA system. And so this is a key part of the work, that if you do a BECCS system, you've got to also consider the biomass carbon footprint. So gathering all this information from our evaluation, we can then formulate this BECCS performance matrix, which kind of summarizes how you might try to optimize the performance of your system, and it all depends what you actually want to do. So, for instance, if you're trying to enhance the efficiency of your BECCS system, you're looking at trying to choose high performance CO2 capture solvents, for instance, with low heat duty, try to recover more waste heat from your system, either through the flue gas or elsewhere. Or looking at choosing, if you're trying to be more carbon negative with your system, then what you're looking at is trying to choose maybe a lower efficiency system, which seems kind of counterintuitive, but that's the case on a per megawatt hour basis, that's the case. Or you can choose a biomass with a much lower carbon footprint. And then lastly, there are some co-benefits when you're co-firing with biomass. You will reduce your pollutant emissions of sulfur, for instance, as we observed in our case. Usually with NOx, you have to be very careful with how you operate your combustion system to make sure you minimize your NOx. So in conclusion, BECCS has the potential to provide negative emissions and From our study, we could show that we could improve the energy efficiency of a BECCS system, so either using heat recovery or using a better CO2 capture solvent. So we showed that we could increase our efficiency from 31% for the MEA conventional system up to 38% if you're using a biphasic solvent with heat recovery. But it's very important with these systems to consider that there's a trade-off between the carbon intensity, the power plant efficiency, and what type of biomass you choose in terms of its carbon footprint. So your inefficient BECCS might remove more CO2 from the atmosphere per megawatt hour, but actually the inefficient system might have a lower dispatch rate compared to high efficiency systems, so then that impacts how well it can mitigate CO2. And so that's the end, and yeah, if anyone has any questions.